Okay. So hello, everyone. Another meeting in which we have 4 lectures by students. The first is Ofri, who will talk about dual diffusion. Ofri, the stage is yours.
Thank you, Mickey. So my name is Ofri, and I'll present dual diffusion implicit bridges for image-to-image translation. This is a paper by researchers from Stanford and NVIDIA, and it was published at ICLR 2023. So we'll talk about the problem statement for image-to-image translation, then discuss Schrodinger bridges and why they classify diffusion models as optimal transport methods, then discuss the DDIBs method that was presented in a paper and see some image-to-image translation results, and finally conclude and offer some possible extensions. So in image-to-image translation, we are given some sample from a source domain, and we would like to find an optimal mapping to some target domain. Some examples for image-to-image translation tasks can be seen down here, such as black and white to color photos, or sketch to photo, or day to night. The original literature in the deep learning era first started off by trying to learn paired domain translation using data sets of examples with source and target pairs. CycleGAN was the first method to attempt unpaired domain translation, and it did so by introducing this notion of cycle consistency, which allowed to train a generator for both domains simultaneously, while learning how to project a sample from source to target and then reproject it back and attempt to minimize the distance between the original example and its reprojection. A later paper called InstaFlow upgraded this notion of cycle consistency to the architecture, and it did so by performing this image-to-image translation using a normalizing flows architecture, which, as we learned, is invertible by design. And this meant that we could go from A to B and back just by the invertibility of the architecture. So the authors of this paper asked what features might still be missing in image-to-image translation models. And one of the main answers they gave to that was removing the need for access to both source and target domains during training time. So why is this useful? Well, first of all, in terms of adaptability, you could think of a situation in which you train some mapping between a source and target domain, but then in later time, you might want to add some more domains into the mix. And this whole notion of now having access back to previous domains and then training between all domains could make it more difficult and resource intensive. So it would be more adaptable if we can do without this connection between a source and target domain during training time. And in addition, if we could remove this dependency, this would also be good for privacy-sensitive domains, such as the medical field, in which we can't actually share between source and target domain, not the data or maybe models. So in addition, they also asked the question, since in image-to-image translation, we actually perform some mapping between one source probability distribution to a target probability distribution function, can we do so in an optimal transport manner? So they also wanted to add this feature to the algorithm. And in addition, they wanted to retain this cycle consistency notion as was brought up in the InstaFlow paper. So this is the architecture they proposed. It's called DDIBs, Dual Diffusion Implicit Bridges. And for now, all that you need to know is that they actually concatenated 2 diffusion models, one that was trained on the source domain and performed a source to latent Gaussian vector mapping, and then another diffusion model that mapped this Gaussian vector to the target domain. And in the next part of the seminar, we'll discuss why this architecture actually offers us all these nice features. So we'll start off with optimal transport. We discussed in this course a lot about how diffusion models actually diffuse one probability distribution into another. But can we ask the question, could that be done optimally? So in what sense? Well, optimal transport is the problem of exactly that, dealing with how to transfer one distribution into another but do it optimally given some cost function. So basically minimizing the expected cost for this transfer procedure. The Schrödinger bridge problem is a type of optimal transport problem in which we also, in the optimization, have some entropy term to it. Now, the specifics of the optimization problem here is quite involved and beyond the scope of this seminar. But what you guys need to know is that the solution to that is a Schrödinger bridge, and it is an optimal transport method. And in addition, it gives us a joint PDF over the path space from one marginal to another. So the authors quote this paper by Shen et al. From iClear 2022, and they quote this theorem of Schrödinger bridge optimality. And what this theorem states is that given that you have found some functions phi and phi hat that answer to this factorization of the density of our marginals, and having these also be a solution to some set of PDEs, then the solution to this very tough optimization problem is this can be expressed by the set of this forward and equivalently backward SDEs. In addition, they also state that the optimal forward and backward policies for these SDEs or this Schrödinger bridge is Z and is denoted by Z and Z hat, which is as can be seen down here, is the multiplication of the diffusion coefficient times the score function of these phi and phi hats. Now, if this looks familiar to you, it's actually because we've seen something like this in the course. And now let's recap exactly that. So as Noam has showed us in the lecture on PDs and SDs, diffusion models or score-based generative models have their interpretation as an SDE, which is given exactly by these two forward and backward SDEs. And in addition, this also has an equivalent probability flow ODE form, which, as can be seen in this figure, is this nice smooth mapping from one marginal to another. This also gives us a unique mapping between one marginal to another, and this will be quite useful later on. So now let's make the connection. So we saw that for SGMs or diffusion models, we have some form of SDE. And in addition, a Schrödinger bridge problem solution also has SD formulation. Now, what Chen et al. Point out is for a specific choice of forward and backward policy, as can be seen down here, then we actually get likelihood equality between SGMs and SPPs. And what this means is that essentially, if we have successfully trained a diffusion model, then we found some form of optimal transport method. And this could be quite useful. So if we look back at the architecture that was proposed, DDIBs is essentially a concatenation of two Schrödinger bridges, one that maps source to latent, and one that maps the latent to target. And both of these sides can be seen as the ODE solvers that map one marginal to another for their specific domain. So that's quite nice. And then the authors then go on and perform specific tests to see this notion of optimal transport within the DDIBs architecture. So what they do is they perform a test of example guided color transfer, in which we have this source image, for example, and one reference image. And we would like to create this target image that's basically the transfer of the color space of this image, of the source image, to the target image. The way they perform that is by training an image-specific diffusion model that trains on the normalized RGB space of the source image, and one diffusion model that trains on the normalized RGB space of the reference image. And then they, via inference through the DDIBs architecture, they get a deterministic mapping from the RGB space of the source image to the reference image. And then they could just replace the color such that we get this nice target image. So what you should be asking yourself right now is, Well, we know that the source to latent could be optimal transport and the latent to target, but does that guarantee us optimal transport from source to target? Well, the answer is no, we are not guaranteed that, but the authors go on and actually test the performance of the DDIBs transport with respect to, in comparison to actual optimal transport methods that performed exactly this color transfer. So methods like Earth Mover's Distance or Sinkhorn that actually do this optimal transport mapping. And what you see right here is that both visually and quantitatively, we have similarities between the DDIB method and the optimal transport methods. So in terms of optimal transport, we can say that DDIBs gives us what we want. Now, in terms of cycle consistency, why do DDIBs actually invoke cycle consistency? Well, the answer is that the deterministic nature of the PFODs, it gives us exactly that. Because if we take some example from the source domain, project it to the target domain, then reproject it to some coordinate x prime, these are equivalent up to some discretization error, because this is the deterministic mapping in the design of the architecture. And they go on and test this by training diffusion models on some simulated domains, as can be seen here. And this is a very nice example that shows us that they take some sample from some source domain, translate it to some target domain, then reproject it back. And you see that both the samples are equivalent. This is also tested by L2 distances. And we can say that the DDIBs architecture actually gives us this cycle consistency that we wanted. Now, what about privacy and adaptability? Well, in terms of privacy, let's say we have this, we have Alice and Bob, and they each have their own privacy-sensitive domain of tigers and cats. Well, according to the DDIBs algorithm, they can each train their own diffusion model, and without sharing data or model, they can perform this image-to-image translation by relaying this Gaussian vector between them, and then they could get this nice transformation from this tiger to this cat. Now, this answers the notion of privacy. But what about adaptability? Well, you can imagine that we could get a third and fourth and fifth and more actors that have their own privacy-sensitive domain. They could just train their own model, and everybody here could communicate via this random Gaussian vectors without exposing any of their data or models. So this is nice for adaptability and privacy. So on its face, we got we've answered all the requirements that the algorithm was supposed to do. But now let's see where things get a bit chippy. So to scale up the difficulty of the test, the authors try to perform class conditional ImageNet translation. And how they do that is they take a pre-trained diffusion model, that was trained on all of ImageNet with classifier guidance. And what they claim is that this classifier guidance that is class specific in conjunction with the pre-trained diffusion model actually gives us 1,000 different diffusion models. And then they go on and test this image-to-image translation between domains. And they do two tests. One is in-breed translation. So like these examples right here, between different breeds of dogs or between different types of cats. And the harder test that they performed was called the multi-domain translation. And in this test, they take a lion, the lion image that you see right here, and translate it to other domains, that being jaguar and tiger, but also dogs and bear. So what they claim is first that in terms of postures and poses, that DDIBs actually performs well in terms of OT distances. What they mean by that is that you can see that the poses of the results are sustained or the same. And they also claim that DDIBs successfully internalize the characteristics of distinct animal species. And what they mean by that is that, say you have an image of a roaring lion, if you translate that to a domain of a jaguar, well, it makes sense that you get a roaring jaguar. But then if you go to a domain of a Sussex Spaniel, then the notion of this tongue hanging out would translate much more sensefully to this type of image. So they claim to have success in these tasks, but this is where I want to raise a slight fault that I think they made here in terms of privacy and adaptability. Well, the requirement was to not have any shared source and target domain in training, but in essence, they took a pre-trained diffusion model that did have this combined training on all domains. So in some sense, the privacy and adaptability didn't hold when they scaled it up to a more difficult test. I don't think this completely faults. This is still a nice notion of concatenating two diffusion models and performing this translation in inference time. And you can imagine a world where there might be like a foundation model, and each one has their own private sensitive data. And through the model that everybody has access to, we could still perform this type of translation. But in this specific case, it didn't exactly hold the way that they required it. Also, in terms of optimal transport, they do share some examples of failed cases, like you see this one in the middle, where they tried to translate from one type of dog to another, and this completely failed, both in every aspect, the background, the dog, like nothing of this translation wasn't successful. And this means that also in terms of optimal transport, we see that the DDIBs doesn't completely hold. But as I said, there isn't a theoretical guarantee here for optimal transport. It's just something that they showed that in more simple case, it actually holds. So let's conclude. DDIBs are a concatenation of two Schrodinger bridges, which are each OT methods. They're based on DDIM in their PFODE version, which gives us a deterministic mapping. And by that, we get the exact cycle consistency. In simple settings, this enables privacy-sensitive image-to-image translation and domain adaptation without requiring access to source and target domains. But we saw that when we scale up the difficulty of the test, the privacy, adaptability, and OT requirements aren't fully solved. In terms of possible extensions, well, one idea could be to take this architecture and move it from the image-to-image domain to multimodal problem. So say image to 3D or image to audio. Another possible extension could be to maybe ease on the requirement of privacy and maybe say that we could have source and target domain shared training, but let's do it on a small set of data. And this doesn't completely botch the privacy requirement because we still would have some shared data, but not everything. And maybe that could be one direction that this architecture could actually fulfill its requirements. So I hope this was interesting, and thanks for listening. And if you guys have any questions, feel free to ask.
Thank you very much. Go ahead.
So can you go one slide back to the... So what makes the two diffusion images share the latent space? So if they're trained completely separately, what makes a latent in one diffusion model correspond to a similar image to the second one?
Well, so that's a very good question. I think that's the whole point, that they showed that in terms of because there is some optimal transport notion here, when they tested this out on something simple like the RGB spaces of images, then translating one probability distribution to another went smoothly when you go through the normal distribution. But when they scaled it up to, say, ImageNet translation, this became much more difficult, and we saw that this didn't actually work. And it worked the only reason it did work was because they did have some shared training between both sides of the DDIB architecture, right? Because both DDIMs did have shared parameters and shared training.
Thank you.
Other questions? Well, thank you very much, Ofri.
Thank you.
Our next speakers, Shelly and the other Ofri. Please upload your slides. Okay, DPS, the stage is yours.
Okay. Hi, everyone. My name is Shelly, and this is Ofri with I. And today we'll present two papers that focuses on solving inverse problems with latent diffusion models. The first paper proposed the algorithm called PSLD, and the second paper proposed the algorithm called ReSample. The PSLD paper was published in NeurIPS, and the ReSample paper published in ICLR. So first, we'll discuss some what are inverse problems, what is DPS and latent diffusion models, because both PSLD and ReSample algorithms solve inverse problems with DPS in the latent space. And then we'll show some experiment of both papers. First, what is an inverse problem? As we all saw in Mickey's lecture, we have a measurement y, and we want to reconstruct the original image x. And we have also the forward operator, which is does the degradation of the image. In linear inverse problems, the forward operator is a linear combination of the matrix A and the image x. So these are some examples of linear inverse problems. The first one is yes, thank you. The first one is in painting, motion blur, Gaussian blur, and nonlinear deblurring. This is the only one here that is not linear. So DPS paper, as Ron mentioned last week, also solves inverse problems, non-linear and linear problems, and it uses the base rule to transform the score function from log of p of x to log of p of x given y. And the main contribution of the paper was to approximate this term to be the Laplacian approximation of to be this term. And this is the algorithm of the DPS. It uses first the DDPM, regular sampling, and also adds this term that is the approximation of log of p of y given x. So latent diffusion models are models that run the diffusion process in the latent space, and their pros are that they the training cost is lower and they do faster inference. These both of these pros are because of the conversion to the latent space, which is lower dimensional than the image space. This is an easy explanation of how latent diffusion models work, and we'll continue. So the main problem of the both papers tried to solve is inverse problems with latent diffusion models. We'll mention that both papers tried to use foundation models like stable diffusion to solve these inverse problems without any additional training. Okay, so we discussed earlier of what is DPS, and this is how the conversion of DPS to the latent space looks like. As we can see, there's only the decoder here and the initialization with Z instead of X, and here you can see the original DPS algorithm. Both papers suggested that there are problems with the vanilla conversion of DPS to the latent space. The problem is that the images reconstructions are often noisy or blurry and can be inconsistent with the measurements. Both papers suggested reason of why this problem can be and how to solve it, and we'll focus now on the first paper, which is solving linear inverse problems via posterior sampling with latent diffusion models, which is the PSLD paper. The authors mentioned that the fundamental reason that there are many images and hence many Z0s that can explain the measurements. We'll mention that this problem is not unique to the latent space, but it's a general inverse problem, and this is one of the critiques we have about this paper. The authors mentioned that the DPS term here can pull ZT in the diffusion process towards any of the Z0s that can explain the measurements and potentially in different directions. And on the other hand, the score function pulls the ZT in the diffusion process to a specific Z0, which is the best denoised version of ZT. Okay, one solution the authors mentioned is to penalize latents that are not fixed point of the encoder-decoder decomposition. What does that mean? It means that we want to generate samples that remains on the manifold of real data, and this is the term that can penalize this. That's because if you want to think of the manifold of real images, if we have a good encoder and decoder, then when we decode and then encode the images, we'll be back to the same point, to the same latent vector that we were, just like Free mentioned in the previous lecture. So this term penalizes images that are not on the manifold of real data, and hence, if they're not on the manifold, the encoder and decoder won't act like a unit operator. Okay. This approach, on the other hand, does not penalize reverse SDs for generating other latents as long as they lie on the manifold of natural images. In the linear case, which is what this paper focused on, this can lead to inconsistency at the boundary of the mask. If you can think of this image, inconsistency at the boundary of the mask means that the image inside doesn't fully adjust to the image that the ground truth image. The authors mentioned that we can solve this by using this gluing of Z0 term, meaning this is some sort of projection onto the measurements, as we saw in Mickey's lecture number 7. The optimal solution to this projection is given by this equation, and in the paper they stated that they use the forward measurement operator such that a transpose is the identity matrix. This gluing object penalizes decoded images that have discontinuity at the boundaries of the mask, as you can think of this term here and this term here. This is the full PSLD algorithm that uses latent DDPM and latent DPS term and adds the additional PSLD term.
Okay, so the second paper is solving inverse problems with latent diffusion models via hard data consistency. We want to note two things. First, it's not only linear, it's general inverse problems. And the second, we would like to emphasize it's hard data consistency, and now we will see what is hard data and what is soft data consistency. So if we'll circle back to the problem that motivated everything, is we got some bad images if we use just a latent DPS, and this paper suggested that the problem lies in the fact that D, the decoder, is highly non-convex, which means you have a lot of local minimas. And this is the problem, the main problem why you got bad results, and they address that in their solution. So as we said, you have soft data consistency, which is basically just use incremental steps. Each time you do an update, you not only do the unconditional update, which is the between ZT to ZT to the next ZT tag. You also use this term, which gives you some data consistency, but it's not enough. So what they added, or what they chose to do, is using hard data consistency, which is basically just solve some optimization problem. You could do it by gradient descent, for instance. And as some of you probably notice, when you do optimization problem, it's very costly. So if it's costly, you don't want to do it every time. So what they notice is that if you do it like only once every few steps, in their paper it was like 10 steps, you get pretty good results and you get less time cost. So the algorithm itself is just like in the PSLD. It starts just like in the PSLD. You start from Z capital T, and you start to reverse process towards Z0. And when you get to time, let's say time step T, you stop. And then you say, okay, now it's time step T. I want to do some data consistency constraint. So what you're going to do is you want to take Y and obviously use it to get a Z0 given Y. But you also going to use ZT. And this is because the local minima that we mentioned before. If we initialize Z to be just any Z, we probably step into a local minima, and they want to avoid that. So what they say is we're going to find Z0 not only according to Y, but also according to Z0 given ZT, which is given by Tweedy's formula. So I hope it's clear. If not, please tell me. Okay. So after we got Z0 given Y, what you want to do is come back to the latent space data manifold, because you want to keep going and continue the reverse process from time T, which is the time step where you stop. So they discovered that if you use only Z0 as a function of Y, you get a very high variance. So they also suggest using ZT tag. And I will remind you that ZT tag is the last sample you got from the reverse process. And now you say, okay, I'm going to use this ZT tag, which contains some of the data from the reverse process. And we're going to use also Z0 given Y, which is the estimation which is consistent with Y. And we're going to use them both to get ZT. And now we get a distribution with less variance, and they proved that the distribution is a Gaussian, such like that. And that it, I think. And okay, from when you get to ZT and you sample, obviously you resample from this distribution, you just keep going along the reverse process. So we know it can be a little bit confusing, so we will just do a quick recap. So you start with a Z capital T, and then you just do the reverse process with unconditional DDIM, and each time you get to a specific time step and you say, okay, I want to do hard data consistency. Again, in the paper it was like 10 steps. They used 3D formula to get an estimation of Z0 given the ZT you got so far. And then they do some optimization problem to get hard data consistency. And afterwards, they can calculate the probability and just resample and get the next step sample, and they continue with the unconditional DDIM step. Okay, so now some experiments. So here you can see the PSLD results from the first paper, which Shelley talked about. So you can see a super resolution task on FFQ-HQ datasets. There is a comparison between PSLD and DPS. I would note that PSLD use stable diffusion as a zero shot without fine-tuning or anything like that. And the DPS is trained specifically for FFHQ. And as you can see, DPS give you some more smooth images, and PSLD, I don't know, like it preserves better the surroundings. Here you can see in painting random on top, and a bit down below you can see just boxes. You can see PSLD again, very nice. Okay, here is some results from the second paper, from the ReSample paper. As you can see, ReSample is compared to DPS, latent DPS, and PSLD, and it's pretty much better than all of them. And we would like to note that there is some inconsistency between the two papers. So the two papers show the results of PSLD, but there is a big difference, a big gap between the results of the PSLD between the two papers, even though you use the same dataset and you do the same task. And there is a little bit of difference in the variance, in the noise variance, but the higher variance is actually in this paper, in the down below. So even though they have worse setup, they get better results than what the second paper showed us. So we do not know whose blame is it, but probably there is some data manipulating or cherry picking, because somehow, according to one paper, the other paper is much worse, and it doesn't, I don't know, doesn't add up. So if we keep going, we can see some more results of the ReSample algorithm. Again, it's really nice. They do not compare to PSLD over nonlinear deblurring, because PSLD, as we mentioned, is designed for linear problems. And if there is no questions, I will go to the critics. Okay. So we have some critics about the PSLD. The main critics is first of all the fact that the problem they mentioned about latent DPS is ill-founded, because what they say is the problem with latent is just a problem with any ill-posed inverse problem, so it doesn't really answer the question. Another thing is the proofs they used, or the proofs they showed in the paper, are kind of toy examples, and they require some assumption which are not necessarily holds for natural images. And in their proofs, and also even in the heuristics of the gluing term, they do not they do not mention the noise, and so it's not very rigorous. So it's another problem. And the ReSample paper has a few problems. The first is the fact that, as I said, the results does not like they do not match between the two papers. So someone did something a little bit sketchy. Another thing is that hard data consistency is very computationally. Actually, they do address it. I mean, they do mention it. They are aware of it, but it is a really big problem. At least we think it is. So we mention it as well. And also, they did not present FID score. So they did mention the LPIP score, but I don't know, it's arguably not enough to know if perceptually their images are as good as anyone else. So is that it? Any questions?
Thank you very much.
Thank
you. You know, we will put the recording in my webpage and then they will sue me for what you said.
On which sentence? I mean, specifically, what?
About the something sketchy that you mentioned.
Okay, yeah. You can address it.
Other questions, guys? Questions? Okay, our next lecture by Nitzan and Tuval on DiffEdit. Please go.
Thank you, Mickey. So we are Nitzan and Tuval, and we will present you the paper about DiffEdit, diffusion-based semantic image editing with mask guidance. It was presented in CVPR 2022 by a group of MetaAI. Okay, so the agenda for today is to show you some introduction, then we'll go through the architecture, we'll see some evaluation tests, some experiments, the contributions of this model, and then we will see some future work. Let's start with some introduction. So DiffEdit is a method to take advantage of text conditional diffusion models for the task of semantic image editing, and we would like to edit the image based on the text query. So just a word about semantic image editing. Semantic image editing is the idea for replacing a specific part of the image while preserving other parts. Until today, it was usually common to use manual masking by outlining the areas to be edited, and it was time-consuming, so we would like to replace it. In our case, we will have, here you can see two examples. We will have an input image, a caption to describe the image, and we will ask for a query. Here, for example, you have a bowl of fruits, and we will try to replace it to a bowl of pears. And we will do it by generating a mask to the specific area to be edited, and we will replace just the specific place that we want to edit, while trying to preserve the background in each image. On the right, you can see another example for replacing the bowl with a basket by generating a mask specifically for the place where we have the bowl. So let's do a quick overview through the DiffEdit architecture. We will have an input. Here you can see the horse, and we will have two queries, two text inputs. One is the query for zebra in this example. We would like to replace the horse with zebra, and we will have a reference to explain what inside the relevant place to be edited. And we can also pass a null token if we don't want to use a reference text. So we'll start with step one to generate a mask through the relevant place to be edited. Then we will do an encoding in step two. We will use DDIM encoding, which is a reverse step to DDIM. We'll explain it to you in details in the next slides. And then we will try to use the latents for the corresponding image after the DDIM encoding and do DDIM sampling for the relevant mask areas to get a zebra just at the relevant place to be edited. And we will use the encoded latents for the background, as I will show you in the next slides. And at the end, we will have an edited image according to the query prompt. Before we dive into the details, I just want to do a recap for some basic concept that we will use in our slides. So as you saw last week, we had a paper on high resolution image synthesis with latent diffusion models. You know the concept, so I will go through it very quickly. we'll have an input, we pass it through a decoder, we'll have a latent vector, then we inject noise, we'll have a noisy latent, and then we use a denoiser with conditioning. In our case, it will be a text. And then we do the reverse steps, the DDIM steps. We go through the decoder to get the output. Another thing that is related for text to image, as we saw in lecture 6 about guided diffusions, is the idea of text to image. Here I quote the paper of Imogen, a text to image diffusion model with an unprecedented degree of photorealism and a deep level of language understanding. And what Mickey showed us is the concept of clip to train the denoiser with text. So what we do, we take a bunch of tokens that related to specific images, and we're training the denoiser, the encoder, to learn the cosine similarity between the embedding of the text to the embedding of the image. And then we can use the denoiser to predict a specific, to give us a prediction based on a specific token. So let's start with step 1. This is the step 1 in high level overview. You can see on the left horse, and at the end we will have a mask M. And now I'll go through all the steps in between. So we start with an image of an horse, and then we inject Gaussian noise. So in this process, we're injecting a different level of noise injection. So we're using different variances between 0.1 to 0.8. And the idea is to get different latents for ZT with different levels of noise. So actually, you can see different latents with noisy images, different latents. Okay, so now we'll go through the next step where we want to estimate the noise, and we'll do it twice, once for the reference text R, which is horse, and once for the Q, which is the query of zebra. So this is the next step. Now we would like to add a conditioning for the denoiser, and we'll do it twice, once for R, and once for Q. And then we estimate the noise. By using the following equation, we actually can use the denoiser once without the conditioning and once with the conditioning. And we have the lambda to control how much guidance we give to the denoiser. So we will have the estimation of the noise. And now we will take the two estimations, once for the conditioning with R and once for Q. And then we're calculating the Euclidean distance between the two for each noise. So actually, we repeat the same process for each noise level. So we'll have a vector of distances for each noise, and then we will average the distances. And then we're doing just technical stuff to convert the image to grayscale. And then applying a threshold to get a binary mask just to the relevant place to be edited. And actually, you can see that it's not perfect, and it is not as it, and it will help us in the future because it will blend part of the rest of the background into the image generation.
Okay, so let's dive into the second step of this architecture, which is the encoder. DDIM encoding is the process of mapping the input image into the latent space. We are all familiar with DDIM as a decoding scheme, and here we present to you a new procedure of DDIM sampling, which is actually a reverse step of the traditional DDIM. So as we are all familiar with the DDIM update rule, which is estimating xt minus 1 from xt through this formula, what I can do is writing this sampling rule as an ODE, which is the following ODE, where u is equal x divided by square of alpha, and tau equals square of 1 divided by alpha minus 1. So this ODE can be solved using the Euler scheme with the following initial condition, where u is distributed as a Gaussian with a variance of alpha capital T, which is the following Gaussian. What we can do is use this ODE to encode the input image x0 into xr, our latent variable, for time step r smaller than 1. By using this following boundary condition on the ODE, which is actually u at time step 0 equal the input image x0. So we will apply this Euler scheme until time step r, which we can see in the following diagram. What we have here is the input image fed into the encoder. Then we perform this reverse DDIM step r times until we result with this xr, which is our latent. What is beautiful in here, which is different than just injecting Gaussian noise, is this DDIM reverse step preserving all the information from the input image. So it can be accessed later on the decoder via the DDIM sampling. Why it is important to us? Because we are in a task of image editing. So we would like to preserve this information from the original input image. Okay, so our third step is the decoder. We are familiar with the DDIM sampling, which is done by this equation of estimating xt minus 1 from xt. But what is added in here is first we are using query. The query here, as for example, in this example, our query text is the zebra. So in each DDIM step, I feed into the DDIM the zebra query, and we can see it here in this equation of yt minus 1 estimated from yt. And here in epsilon theta, I feed inside the query. So each DDIM step is conditioned on this query. And what I also do in here is using this mask. All the pixels outside the mask, I want to preserve them from the input image. So they are not conditioned on the query. So I actually put in here this null character. And inside the mask, I want actually to change the object to be edited. So I use this xt from the DDIM reverse step, and this is what I preserve from the outside the mask. So here we can see the top view of the whole architecture. As we saw, we have the input image, we have a query queue, reference, text. We compute the mask using the injection of different Gaussian noises. We compute the normalized difference. We have the mask M. Then we do the encoding using the new procedure called the reverse DDIM step. And then we feed this latent XR into the decoder, keeping the background as is, and inside the mask, I conditioned on the query, which is the object to be edited. Okay, so how do I evaluate image editing task? So we have three main evaluation metrics. The first one is the LPIPS, perceptual distance, which is measuring the similarity or distance between two images. This metric is based on human perception. A lower score is better. The main idea is actually feeding two images into CNN or other networks. I use their feature maps. I normalize within the channel dimension. Then I scaling using a W vector, and I compute the L2 norm of the two images, and then this is my distance or similarity measure between the two images. We also have a metric called CSFID, which is actually an extension of the standard FID, but it conditioned on the class. So the following formula is computed per each class, and then we take the average along the classes. The third metric is the clip score, which is a metric that actually computes two embeddings. The first one is for the image caption, and the second is for the image. And within the embedding vectors, I compute the cosine similarity, and then I use this scaling just for interpretability. And this is a metric to evaluate how well a generated image caption match the actual image. So let's see some results. Here we can see the ablation experiments on ImageNet. So we keep in mind that LPIPS and CSFID, these are two metrics that lower scores are better. So we can see that the DiffEdit outperforms all other methods. We can see here in the ablation studies, the DiffEdit without the encoder performs worse. So the encoder technique of the DDIM reverse step has an high impact. Here we can see the different threshold values of generating the binary mask. So if I take a high value for the threshold, it results in a worse CSFID, which is an overestimation of the binary mask. And the smaller threshold will result in an underestimation of the mask, which cut the object boundaries. Here we can see some results of the ImageNet, which has labels. So we use the CSFID score along with LPIPS. We can see also in here that the DiffEdit outperforms all other techniques. We can see some beautiful examples. Here we see these women and the background, and in the SD technique, the background is totally different, and the woman is different. And here in the DiffEdit, we preserve all the background, and just the dog is different in here. And we can see other examples. Here we have the ImGen dataset. This dataset doesn't have a label, so we cannot use the CSFID score. But we use the clip score along with LPIPS and the regular FID score. We also see the DiffEdit outperforms all other methods. We can see here in the example how DiffEdit performs better in a visual manner. Here we have some results on the GOCO dataset, which are natural images without labels. And here we also can see in the graphs how DiffEdit outperforms all other models. It also without the reference text, so it's another improvement. Okay, so to summarize, the key contributions of DiffEdit is first the automated mask generation. As in previous methods, we needed to do this manually, and here it's an automated generation. It's a text-guided editing. We can use the prompt to control the diffusion process and the precise modifications within the images. It allows us lighter edits where we conserve more information from the input image, which is important in an image editing task. And it outperforms the previous approaches on the different data sets as we see.
So let's talk about some future works. We looked at the model and we tried to think what can be weak spots in the model. So we took the code and we tried to generate multiple masks. And we saw that if we choose objects that in the background, for example, you can see that we try to generate the query for sand and replacing the grass with sand. It was not performed very well. And then we saw that the noise, if we look on the left, you can see that the noise is capturing also the place for the horse. So actually, it's something that we wanted to solve. So we suggest to improve step 1 by using multiple masks with n prompts. So we're actually doing the masking n times, and we inject noise. We inject noise to the input image, and then we pass the denoiser with n different prompts, and we generate weight for each mask. And the idea is to get a higher weight for front masks. And you can also see that we have much more noise in the place for the zebra or the horse. And when you look at the stand, you can see that the noise is much lighter. So by using different weights, depend on the amount of noise in each pixel, we can actually generate different weights for different parts in the image. And the idea is to then use the weights that we calculated and adjust it to step 3. And when we do the DDIM decoding, to use the weight that we just created, and to do the decoding using the weights. So if we are looking on the relevant equation, you can see that we are generating on each step, we generate the YT tilde with the mask that's relevant to a specific query I with weight I. We take the YT, which is the previous decoding step, and we take from the encoding the rest of the picture for each mask. By doing that, we can preserve the background for each image, but still get very good results for different parts in the image. And we took the idea from the very similar idea of multi-diffusion, which is another paper that they are suggesting just choosing different patches in the image and use multiple queries and then update them simultaneously. So the idea here is to take advantage of the method of DiffEdit, which you can identify the patches by injecting noise into the picture. Okay, that's it. Any questions?
Thank you very much. Questions?
Thank you.
Okay, great. Please have a meeting with Noam to talk about this future direction and fine-tune it. Wonderful.
No problem. Thank
Okay.
you.
Okay, and our last speaker is Nadav, who will talk about flow straight and fast. Nadav.
Thank you. So I will present this paper, Flow Straight and Fast, also known as Rectified Flow, by Xingqiu Liu and Chengyu Gong from the University of Texas Austin. So the objective of this paper is to find a transport plan between two distributions using an ordinary differential equation, an ODE, with the key idea of flowing as straight as possible. The reason we're interested in flowing as straight as possible is for two main reasons. One reason is that solving ODEs that behave in a straight manner is very easy to solve numerically with little to no numerical error. And also, they prove in the paper that a straight path reduces the transport cost, and it is indeed a necessary condition, but insufficient of optimal transport. So here I show an demonstration of the difference between an SD and an ODE. On the left, we can see solving a diffusion problem using DDPM. And on the right, we can see using DDIM. So the difference is the Gaussian noise or any other kind of noise that is being added in the solving process. So this paper uses an OD approach even during training, which is very different than most of the diffusion methods we've seen this far. So what do I mean by a transport plan? So giving two distributions, pi0 and pi1, I want to find a transport plan, which is a function t, that maps one distribution to the other. So assuming I have Z1, Z0, which is a cluster of points drawn from the distribution pi0, then I want to find a function t, that t of Z0 would be equal to Z1, which is a cluster of points drawn from pi1. If we have this transport plan, we will denote Z0 and Z1 as a coupling or a transport plan of pi0 and pi1. I'd like to note that there is a slight difference between a coupling and a transport plan. A coupling is more like a discrete version of a transport plan, but I will use them the same for this talk. So each transport plan has a transport cost. So according to optimal transport, we know that the cost of a transport plan would be the expectation over the function c of z1 minus z0, where c is some convex function. In this paper, they use the L2 norm. So we can think about it as going through all the pairs of points in the transport plan, x0 from z0 and x1 from z1, and calculating their L2 norm, their numerical distance, and then averaging it. So that would be the transport cost of a coupling. So what are some applications of transport plans? We can use it for generative modeling, just like regular diffusion models, where we're giving pi1, which is a distribution of some data points or images, and we will decide that pi0 would be some easy to sample from distribution, like a Gaussian distribution, and then we would map the Gaussian distribution to the data distribution, and we could sample from the data distribution. Or we can use it for transfer modeling. For example, if I have images of cats and dogs, I could map the images of cats to images of dogs and vice versa. So the method they chose to implement this transfer plan in this paper is using to learn a vector field V, which would be equal to d of zd, where z0 is drawn from pi0 and z1 is drawn from pi1. In this paper, they chose the dzt to be the linear interpolation between the two clusters. So assuming I have x0 and x1 in the transport plan, and x0 is drawn from pi0 and x1 is drawn from pi1, then xt would be the linear interpolation between the two. So dxt would just be x1 minus x0. So I'd like to also to note that in contrast to diffusion model, where we define a forward process and invert it, here there is no forward process per se. We define the score function, if you want to think about it that way, and then try to emulate the score function we have defined. So to learn this vector field, we can just use a conditional expectation. So we would want that the vector field v at the point xt and t would approximately be the expectation of x1 minus x0 given xt. Assuming that xt is the linear interpolation between the two, and the two are in the transport plan we want to learn. So giving a coupling, we would learn the vector field by minimizing this very simple loss function. It's the integral over all the values of t, and the expectation over all the pairs x0 and x1 that are in the coupling. And we would just take the L2 norm between x1 minus x0 minus the vector field at xt and t. After we have trained our ODE, how can we sample the transport plan? We will simply solve the ODE using any ODE solver, for example, the Euler method, by using dxt to be the vector field we have learned. So if we want to use the Euler method, we start with x0 from z0 or pi0. In the generative modeling case, it would be just a Gaussian distribution, and we would update xt according to this simple update rule. Basically, it means flow according to the vector field you have learned. So until here, it's very, very simple. And now we start to get to the main contribution of the paper. So an important property of flow in the ODE case, in the deterministic case, is that the flow cannot cross. It avoids crossing. What do I mean by that? Is that there cannot be two trajectories that meet at some point Z in the middle, and one would end up in one target, and the different trajectory would end up at a second target. Why is that true? You can think about it in two ways, which are actually the same. So we have an ODE, and the ODE is very simple and has a unique solution. So we cannot solve the ODE and get two different results, just in contradiction to the fact that the ODE has a unique solution. Or if you want to think of it more simply, the flow direction, which is a vector field of xt and t, it depends only on xt and t, and it is deterministic. It's an ODE. We don't add any Gaussian or other type of noise. So at each point, we go in a single deterministic direction. So we cannot go in a point in the middle and end up in two different points. So because the flow avoid crossing, what we would get is behavior that looks like this. So here we have a very simple example. We have two distributions, the purple distribution and the red distribution. And on the left, we can see how it would look to linearly interpolate between the two. If we would train a rectified flow model up to the point I've just shown, we would get this behavior. So the model would try to emulate the vector field to the best of its ability, but it cannot cross like the linear interpolation. That would mean that when it approaches the crossing point, it would deviate to a different path because it is infeasible for it to cross. So all the points in this cluster would end up in this one, and all the points in this cluster would end up in this one. What we would want is to end up with this type of flow, which is straight. So how can we do that? Given a transport plan, Z0 and Z1 from the two distributions, how can we find a better one? So the main contribution of the paper is this mini algorithm they called Reflow. So what does Reflow do? So it gets as an input a vector field that's been trained on some transport plan. Let's denote it Z0 and Z1. And it would get also as an input Z0 tilde. Z0 tilde and Z0 share the same points. They are exactly the same up to a permutation. And then we would solve the ODE DZT equals the vector field starting from Z0 tag to get Z1 tag tilde, and we return Z0 tilde and Z1 tilde as a new transport plan. I will later show you that the new transport plan has a lower or equal transport cost to the old one. This algorithm is very important to understand the paper. So is there any questions about it? Good. So why does it straighten the path if I use this method? So as we show, flow avoids crossing. The vector field cannot cross. So what happens if I reflow according to the vector field that was trained on some transport plan? Then each crossing path that was in the original transport plan will not be present in the new one. So if I have a new transport plan that is free of any crossings, and what would happen if I would retrain a rectified flow model on this new transport plan? Then there would be nothing to stop it from converging to DZT, which we define to be a linear interpolation, which would result with a straight path between Z0 tilde and Z1 tilde. There is a rigorous and theoretical proof that after reflowing many times, they do converge to a completely straight flow, but I did not include it in here because it was too rigorous and mathematical, but if you're interested, you're welcome to check in the paper. So I don't know why my computer shows the animation so poorly. All right, you can see here an example of training rectified flow and then reflowing it. And we can see two interesting things. The first thing is that the flow of points on the right after reflowing and retraining the model is significantly straighter than what we see on the left. But very interestingly to me, we can see that the vector field that is shown by the little gray arrows on the background stays relatively constant during the sampling process, while it changes more rapidly before reflowing. So that shows us the importance of the transport plan. And to prove that the transport costs indeed decreases, I want to briefly talk about marginal distributions. So what are marginal distributions and why we're interested in them? So if this transport plan is the result of reflowing the vector field V that was trained on this transport plan. Then the marginals of ZT tilde are equals to the marginals of ZT. What do I mean by marginals? I mean, when we flow starting from pi 0, which is the distribution of the Z0, up to time t, what distribution do we get? And what distribution do we get when we start from Z0 tilde? So the reason we can easily claim that they are equal is because we said that Z0 and Z0 tilde are equal up to a permutation. They are the same points. And the marginal of ZT and Z tilde t is just flowing according to the same vector field up to time t from the same points. And because the permutation does not affect the distribution, and we can say that the marginal distribution of ZT and ZT tilde are the same. So how can we prove that the transport cost indeed decreases after reflowing? So let's assume that Z0 tilde and Z1 tilde is the result of reflowing the vector field V over the transport plan Z0 and Z1. So what we see here, this expectation is as we define the transport cost of the new transport plan. From the definition of flow, we can replace Z1 tilde minus Z0 tilde with just the integral over the vector field, because that is how we train the model. It tries to emulate this exact vector field at each point, the time step, and assuming it has converged, it is what we get. So from the Jensen inequality and the convexity of C, as you remember, we defined the cost of a transfer plan to be defined with a cost function C that has to be convex. We can insert C into the integral. And the reason we can do that is also because we can think about this integral as calculating the expectation over a uniform distribution of T. Now, what we showed before is that the marginals of ZT and Z tilde T are equal. So we can replace here Z tilde T with ZT. And then we can open up the definition of the vector field to be the conditional expectation that we showed before. Then again, from Jensen inequality in the convexity of C, we can insert C into the expectation. And then using the smoothing property of the expectation, we can remove the conditional expectation to be just a regular expectation over Z1 minus Z0. And then we can see that this expression is not dependent on T, so we can take it out of the integral and we get the transport cost of the old transport plan. So to summarize, we've shown that the new transport plan has a lower or equal transport cost according to every C relatively to the old transport plan. This is true because of the Jensen inequality. Are there any questions about this part? Good. So what's the overall workflow of a rectified flow? So we start from two distributions, pi 0 and pi 1. We're either given 1 or 2. And we draw a random coupling of the two, Z0 and Z1. We fit a vector field to match the linear interpolation between the two. And then using reflow, we find a new coupling from Z0 tilde and Z1 tilde. As we show, this new coupling has a lower transport cost and is straighter than the old transport plan. And then we fit a new vector field to it. And we can go back to step 2 or just and return and retrain it, or just return the vector field and the transport plan. So
just a quick question.
Yes.
In step number 2, when you fit V theta, do you assume that the elements of Z0 and Z1 are paired?
Yes, that is the entire
okay.
concept of rectified flow. I'm sorry if I wasn't clear about that. A transport plan between the two, meaning that each item from Z0 has a specific target in Z1.
Wonderful, thank you.
So the new transport plan is straighter and has a lower transport cost. So before I show results of this reflowing approach, let's briefly talk about how do we measure straightness. So how they defined it in the paper, they define this measure. So we'll define bold Z to be the set of all the marginal distributions, ZT. And the measure of straightness would be this expression, which is the integral between 0 and 1 over T of the expectation of the squared norm of Z1 minus Z0 minus the derivative of ZT. Now, I know it can be a little daunting, so let's break it apart very simply. So basically, we go, this expectation goes over all the pairs x0 and x1 that are in the transport plan. So we have the pairs, and z1 minus z0 just draws a straight line between them. So now we will take a look at what trajectory we have found between x0 and x1. And at each point in time t, we would look at the derivative. So the derivative is actually the tangent. So we will look at the tangent and compare it to the straight line. So if we have that the two trajectories are equivalent and both are straight, then we would get the line between x0 and x1 at each point, and this measure would be 0. And if not, it would measure how much we deviate from a straight path. So considering this measure, we can see here on the two examples they showed in the paper what happens when we reflow multiple times. So here we just train the rectified flow algorithm on a random coupling, and we see that because it is a very simple problem, it does find a transport plan, but it is far from having a low cost or far from straight. After reflowing and retraining the model, we can see that the flow is significantly straighter and the transport cost is significantly lower. We can see that here in the measure of straightness and the transport cost on the right. But still there is room to improve. And then after retraining it once more, we get this transport plan, which is much straighter and has a lower cost. And as we have shown before, that each time we reflow, the transport cost is lower or equal. We can see this also true here in the graph where they did many reflow steps. So I don't know if you can see the animation on my screen, but here I ran a simple experiment when I did 0 reflows, 1 reflow, and 2 reflows, and we can see that the more times we reflow, the straighter the flow, and more the vector field stays more constant as time goes by. So the last improvement they suggested was to, after finding the final transport plan, Z0 star and Z1 star, is to distill it using a separate model. So we found this matching, this coupling. Now we can just use this coupling to train a fast-forward model to map Z0 star to Z1 star directly without the need for a vector field or an ODE. So how does it look on some real world use cases? So they showed in the paper 2 problems. They mapped Gaussian noise to images of cats or images of people to images of cats. They must have really liked cats. I can relate. So here we have 1 rectified flow and 2 rectified flow, which means how many times they did reflow and retraining. So after reflowing once and retraining, we can see that even using a single Euler step, we get something that starts to look like a cat, which is significantly better than the results we get from traditional diffusion model, which take a lot of sampling steps to start to see the image behind the scenes. And after reflowing and retraining again, we can see that even after a single step, it starts to look like a very good image. And using the transport plan that we achieved on both approaches, distilling results in very high quality images in just 1 step. We can see the same results also on the second domain. Some interesting numerical results are, we can see here, they trained 1 rectified flow, meaning reflowing once, reflowing twice, and 3 times. And they calculated the FID once using the Euler solver, and once a single step, and once just running the distilled model. So what we can see is the more we reflow, the straighter the paths we get. And using a single Euler step, we get a better FID. But interestingly, we can see that the distilled model using 3 reflows is slightly worse than using 2 reflows. And when running a full Euler solver simulation of the 3 models, we can see that actually the FID gets worse and worse the more times we reflow. So what's happening here? Didn't we just say that the more times we reflow, we get straighter results and it's better? So we'll talk about it in just 1 second. We can see also in the result that straight after reflowing, they see a bump of performance. So basically the FID drops and the recall score just jumps up slightly right after reflowing and during training, which just emphasizes the importance of the transport plan when training an ODE. So some pros and cons of this approach. So it's very good for fast generation, as we can see also using Euler method or the distilled model, we can sample in few steps or even just a single one. And I didn't talk about it too much, just to be quick, but the straight flows also allows for meaningful latent manipulation. What I mean by that is that closed locations in pi1 are mapped to closed locations in pi0 and vice versa. So meaning that if you move slightly, you move in the noise domain, you also move slightly in the image domain, which can be very useful for image manipulation, inverse problems, interpolations of images, and so on. They showed some unsuccessful examples in the paper, but there are follow-up papers to do it much better. And one interesting benefit of this method that is bidirectional mapping, meaning if we mapped pi0 to pi1, we did that by emulating the linear interpolation between pi0 and pi1. So if we take our vector field model and we just add a minus sign, we can flow from pi1 to pi0, which can be very, very useful. So if we train the model to map cats to dogs, we also train the model to map dogs to cats. But there are some major problems with this approach as well. So the first very difficult problem to solve it requires very long training, because every time we reflow, we need to retrain our model because the source and target distribution changed a bit. So, and we also want to straighten the paths and reduce the transport cost. So that is a big problem. And also reflow is almost infeasible for a large data set, because what we need to do each time we reflow is resample the entire data set through the model. So it can take a while. And if the model is in its early stages of training, we need to use many samples to many iterations to sample it and get a meaningful result that is close to our target data set. So in this paper, they only showed it on relatively easy data sets because it is very difficult to train on large ones. But the main deficit of this paper is that reflowing incurs an accumulative error. What I mean by that is when we start from pi0 and we do the reflow, we start from images that are in the distribution of pi0 and we reflow to pi1 and we don't get exactly to pi1. We have error due to the model error, or our numerical solvers induce some numerical error, and we don't get to the data manifold exactly. We get very, very close. And then when we retrain our model, the next model deviates slightly from that, and again and again. And each time we reflow, we deviate from the data manifold more and more. So that is the reason we can see that the more times we reflow, actually the results deteriorate when we do a full simulation, and also the distillation model starts to deteriorate because our transfer plan doesn't reach the data manifold. It reaches very, very close, but not exactly. So that's a very important note. So if I have time, I would like to briefly talk about InstaFlow, which is a follow-up paper that merges rectified flow with stable diffusion to distill it. Do I have time, Mickey?
Yes, yes.
Thank you. So InstaFlow is a paper by the same author from the University of Texas, Austin. And what he wants to do is to distill stable diffusion. We're all familiar with the model of stable diffusion, and we want to find a model to sample the image distribution using a single step. So what the naive approach could be, we would sample n images from the distribution from stable diffusion. We would sample n noise sources. We would pass them through stable diffusion, and that's how we'll create the data set. And then we would train a model to map the noise to the image in a single step. To make things easier and fast, we would just initialize the model weights from stable diffusion, and we get terrible results. So what can we do differently? We can sample the same data set once again, but this time we would train a rectified flow model, and we would use reflow to straighten the paths that the model takes. And we will again initialize the model weights from stable diffusion for faster training, and we will get significantly better results. So what is the overall workflow? We start from the data set we get from the stable diffusion model. If we just distill it, we get very bad one-step generation. If we reflow and straighten the paths and distill it once more, we get very good results. So we can see here stable diffusion sampled using 25 steps. And here on the right, we can see after 3 rectified flow plus the distillation model, we get very good results, but in a single step. So that's a significant improvement. If we look at the numerical results, we can see that stable diffusion always wins in the FID score, but the inference time is almost 3 seconds to sample a single image. Using rectified flow plus the distillation, we can get in about tenths of a second, which is 2 orders or 3 orders of magnitude speed up, and the results are worse, but not the worst in the world. They are pretty decent. And that's it. Are there any questions?
Thank you very much.
Thank you.
I have a
Questions?
small question. If nobody else
Yes.
has anything. Okay.
Yes.
Did they compare in the InstaFlow paper or in the original paper to other distillation methods?
They did not.
Okay.